Hello students, last time we did electric field intensity and electric field lines. We started with the electric field intensity where we have considered a simple case where the source was kept at the origin and the electric field intensity at point P was given by E is equal to K source upon the square of distance between test and source and R cap, which is the direction from O to P, because the point P will be repelled away. It is a test charge and test charge is a unit positive charge, or test charge is as small as possible as compared to the source charge. Also I have given you the homework where I changed the position of a source charge. Now this capital Q is a source charge which is now having a position vector R dash vector. Now again we consider point P whose position vector is R vector. If you remember Coulomb's law in vector form, we will be joining the line from source charge to the test charge. So I kept the arrow head towards P because the test charge will be repelled away. So this will be the direction of electric field intensity, because the electric field intensity is always in the direction of the force acting on the test charge. Now using the Coulomb's law, F, finding the F and dividing it by test charge, the electric field intensity comes out to be K source, and if you remember it should be the force acting on the particle's position vector minus the force acting on the, here it is a source charge whose position vector is R dash and mode of Q. R minus R dash mode का Q आ जाता है. So we have applied Coulomb's law in vector form. This is the case where the source was at origin, and it can also be written as K source R square. Now unit vector can be written as vector divided by its magnitude. So it comes out to be KQ R vector upon RQ. Now check this. If this capital Q or the source comes at the origin, R dash becomes 0 and the expression turns out to be K Q, R dash is 0, so R vector divided by mode of RQ. So these are the two expressions when the source is at different position, and in the characteristic of electric field intensity we have written that the electric field intensity depends on the magnitude of the source charge as well as the configuration of the system. When I say configuration of the system, I mean what are the position vectors of test charge and source charge. So this was the electric field intensity. Then we have moved to the electric field lines. The simple definition of electric field lines was a pictorial representation to understand the electric field and electric field intensity. Now this field lines concept was given by Faraday, and we define it as a path followed by a test charge if it is allowed to move freely. So to understand this, we have taken plus Q charge as a source. Again we are revising the thing. So if the source is positive, if I place test charge anywhere near it, it will be repelled away. So all these positions where the force was repelled away was denoted by an arrow, and the length of the arrow indicates the strength of the source at that point. And as we move away, the strength also keeps on decreasing, or intensity keeps on decreasing. So we have drawn the electric field of a point charge to be spherical, then the arrow which indicates the strength, more is the length of the arrow, more is the magnitude. Now I am moving away, so length becomes smaller. So I will draw another concentric sphere. This is smaller arrow. Now this thing happens every side or all the sides, the field lines are emerging. Similarly, the arrow length will be drawn small if we move away. If you move away, again the length of the arrow keep on decreasing. So this information help us to find out whether the source is positive or negative. And we have concluded that if the source is positive, the field lines will be emerging from it in all the direction. So this is what the source says. So it is not necessary now to draw a source. Simply I put a point, and if from that point the arrow are emerging, then your source is positive. And by seeing the length, we will see whether the intensity is more or less. And at a point, if a line are entering towards that point or terminating at that point, so this is emerging from a point, they are terminating at a point, it means your source is negative. So from the arrow, we can say whether the source is positive or negative. As we know, the test charge for convention is always taken to be a unit positive charge. Now this were the field lines which were taken as a straight line. The arrow was drawn as straight. Electric field lines can also be a curve. Now in what situation the electric field lines becomes curved? Now let us consider let us consider a system of two charge, say one positive and one negative. In the coming days, this system of two charges which are same in magnitude but have opposite polarity, one is positive and one is negative. Remember, it is not a plus charge or a minus, it is a system like NaCl. So Na is plus and Cl is minus, so it is a system. In the coming days, we will be calling this system a system of two equal and opposite charge separated by a finite distance, will be referred as electric dipole. So that is our next topic, which we will be doing in detail. Now we have to draw the field lines of this. Now drawing the field lines, we will see that the electric field lines comes out to be a curve. Now how to draw the field lines for such a system? This is a system where we have two equal and opposite charges separated by a finite distance. Now to draw a field line, suppose I keep test charge here. Now this is a system. This is a system. Now if I keep a test charge here, there will be a force of repulsion by this positive charge, and there will be a force of attraction by this negative charge. Because you are near to the positive charge, the magnitude of repulsion will be more as compared to attraction. So resultant comes out to be, the field lines will be outward. Similarly, if I keep my test charge at this point, again there will be a force of attraction by this negative charge as compared to the force of repulsion, which will be there but its magnitude will be less. So again the arrow will be drawn towards the negative charge. Arrow always indicate the path where the test charge will move if it is allowed to move freely. So this point indicates if I place a test charge here, it will move towards negative charge. If I place a test charge anywhere at this point, it will move away. Test charge is taken as positive. So these are the field lines. Suppose I put a point here. Now there will be a force of repulsion. So this is the force of repulsion. This negative charge will attract it. So this will be the position. This will be the path of our test charge. Now there are, at this point, we have two directions. One is a force of repulsion, one is a force of attraction. So we need to apply the superposition principle, which will give you the resultant, and the resultant comes out to be in between. But because we are near to the positive charge, this magnitude will be more. So resultant will be near to this line. So this is ER for resultant. Now how should I draw the field lines for this? So I rub these two original directions. So I am rubbing these two original directions, and this was the point where I placed the test charge. So I will join it will come out to be a curve. Similarly, now I remove this portion. Now I keep a test charge at this point. Again, there will be a force of repulsion. There will be a force of attraction. Now, if I am moving away from this and approaching the negative charge, this magnitude will keep on increasing. So, my resultant will move towards this. So, suppose this is the resultant now, away from this, little bit away as compared to that point P. So, this is ER. This is I am explaining you the method. Now, I remove the original directions. Now, this is the point Q say. I remove this also. Now, I join this line. In this way, we have to keep on the test charge at various positions and you have to find out the result. Now, what will be the final situation? It will be like this. As you know, you have seen the magnetic field lines in the standard 10, where from the north pole the field lines were emerging and it comes to south, inside it move from south to north. Here, it will not move inside because it is a system NaCl, Na plus Cl minus, they form a bond according to the chemistry. We are not dealing with the bond formation. For us, it is a system of two equal and opposite charge separated by a finite distance, because when the bonds are formed, there is some finite distance where this bond is possible. So this is our finite system. So this was a field line initially drawn. Arrow means, remember arrow means the motion of a test charge if it is allowed to move freely. Now I get the point test charge at these different points. If I keep on joining that resultant, it comes out to be a curve starting from the positive charge and terminating at the negative charge. Similarly at this point. Similarly like this. Similarly like this. Similar to the magnetic field lines. But magnetic field lines, we will see they form a closed loop. They will emerge from north to south. Inside the magnet, they move from south to north. Here inside is not, it does not form a closed loop. Again this. Now this point later on will be referred as axial point along the axis. So it is straight line. Otherwise, if I keep a test charge here, it comes out to be like this. So see the direction of arrow. This is the arrow which indicates the motion of the test charge if it is allowed to move freely. So your electric field line is now curved, and for a point charge, if your source is a positive charge, it was radially outward. It was radially outward. So this was radially outward. And the path was straight. And if our source is negative, the field lines are radially inwards. So now onwards, it may be possible we will not be drawing this sources if from any point the field lines are radially outward. At that point the source should be positive. If the field lines are entering at any point or terminating at any point, the source should be negative. And if you have a system of two charges, this is system of two equal and opposite charge. So this is how the field lines are formed. These field lines are curved. Now how does this curve is formed? So this was our point P, which we have drawn earlier. Then I keep a test charge at this point Q, and this tangent to this point is your resultant. Tangent to this point was our resultant. तो जो resultant हम बना रहे थे, उनको join करते जाते हैं तो curve आ जाता है. So, if your field lines are straight, there is no question of any direction. You can see the arrow, and you can easily see it is radially outward or radially inward. But if any field line is curved, say like this, and if I say what is the direction of electric field intensity at point P, so simply you have to draw a tangent, and this is a tangent. Remember, which is the resultant of the repulsion by the positive charge and attraction by the negative charge. If I draw a point at this, say R point, so again the tangent should be drawn like this. So this is again the resultant of repulsion by the positive charge and attraction of the negative charge. Because you are moving towards the negative charge, attraction will be more, so this resultant comes out near to the negative charge. So your electric field lines can be straight or curved, and we sum up. If our source is positive, the field lines are radially outward, and if source is negative, the field lines are radially inward, and the electric field shape is spherical for the point charges, and for a system of charges, say plus and minus, we have the field lines to be curved starting from positive terminating at negative. So you will see the arrow from positive, again the arrow is emulsive, and at the negative it is terminating. Now this is a curved electric field line, and at any point if we need to find out the direction of intensity, simply you draw a tangent. So we change our definition again. Initially I said the pictorial representation of electric field is known as electric field lines. Then we say electric field line is a path followed by a test charge if it is allowed to move freely in the electric field of a source charge. जो भी रास्ता टेस्ट चार्ज फॉलो करता है, अगर उसको फ्रीली छोड़ दे तो. Now for this particular case where the field lines are curved, I will again write the definition. Electric field line is a curve drawn in electric field, मतलब inside the region of that charge. So electric field line is a curve drawn in electric field. Electric field किसकी होती है? Source की. Electric field of source charge in such a way that tangent at any point on curve gives direction of electric field intensity. So if you ever find the electric field lines to be a curve which we have drawn in the electric field, then the tangent at any point on the curve, you draw a tangent at any point, and that tangent will give you the direction of electric field intensity. So this is what we have for electric field intensity. Now as we have done the characteristics of electric field intensity, we also have a characteristics of field line. So we conclude by the characteristics of electric field line. So this is another a small important conceptual topic where we will try to understand the characteristics of electric field lines. The electric field lines first characteristic is that the electric field lines emerge from a positive charge or starts from a positive charge and enter or terminate at the negative charge. So electric field lines start, or we can say emerge from positive charge. So it should be positive. Electric field lines start or emerge from positive charge and ends, E-N-D-S, ends or terminate at negative charge. So if you have a system of two charges, it will always start from positive charge and ends at the negative charge. For a point charge, point charge. It can start or end at infinity. अगर सिंगल पॉजिटिव चार्ज है, अब सिंगल पॉजिटिव चार्ज की फील्ड लाइंस कैसे बनाई थी? रेडियली आउटवर्ड. This is radially outward. So it has started from a positive charge, but where it will end? So we assume it will end at infinity. Similarly, if I draw a source charge to be negative, single negative charge, so all the field lines should end or terminate at the negative charge. ये terminate हो रही negative. But from where it has started? So it started from infinity. So if you have a single source charge or a point charge, the field lines can start or end at infinity. For a system, it should start from positive and terminate at negative. So this is the first important characteristics. Second important characteristic: two field lines never intersect each other. दो फील्ड लाइंस कभी भी इंटरसेक्ट नहीं होती है. Now why it does not intersect? So if you have seen the definition which we have written in the end, it is a curve drawn in an electric field in such a way that tangent at any point gives the direction. तो एक अगर इलेक्ट्रिक फील्ड लाइंस बनाई हुई है और फील्ड लाइंस कर्व है, तो tangent gives the direction. Now suppose these are the two field lines intersecting. Arrow indicate the direction of the test charge. तो इसकी arrow इस तरफ है, इसकी arrow. Now these are the two field lines. Now they are intersecting at this point. Now at this point, because the two field lines are intersecting, I will be drawing the two tangents. One tangent will be like this. That is the tangent of this field line 1, and another tangent should be like this, which is the tangent of a field line 2. Now at a point we cannot have the two directions of electric field intensity. If any vector quantity is there at a time, at any particular instant, it cannot have two directions. So if two field lines intersect at a particular point, two tangents can be drawn. And if two tangents can be drawn, from definition, the tangent gives the direction of electric field intensity. At a particular point, two directions are not possible. So two field lines can never intersect each other, because if they intersect, I am saying the reason for it, you have to remember this: two field lines can never intersect each other, because if they intersect, then at the point of intersection there are two tangents indicating the two directions of electric field intensity, which is not at all possible. So second characteristic is important, where the two field lines can never intersect each other. The third is electric field lines never form closed loop. So they never form a closed loop. Now we will discuss this characteristics also when we will be doing the magnetic field lines. So there, for a magnet we have magnetic field lines, and I said earlier, in the magnets, the magnetic field lines emerge or starts from north pole, and it does not terminate at south. Inside the magnet, the magnetic field lines are south to north. But in the case of the electric field lines, if we have one plus and minus charge, it starts from positive and terminate at the negative charge. It is not possible that it form this closed loop. ऐसा नहीं होता है कि पॉजिटिव से स्टार्ट हुई नेगेटिव और नेगेटिव से वापस पॉजिटिव की तरफ. The field lines are always from positive to negative. पॉजिटिव चार्ज से स्टार्ट होती है और नेगेटिव चार्ज पे टर्मिनेट हो जाती है. So they never form a closed loop. So while studying the magnetic field lines, we also come to this point again. Fourth, in a charge-free region, electric field lines are continuous curve without break. Now what does this mean? If we have only the system of two charges, I will draw this field lines as a continuous. The field lines are continuous. It is not drawn like this. This is plus charge, this is minus. The break of a line is not possible. So it is a continuous curve if any other charge is not present in the system. We are considering two systems only. Also, if I consider one system, I will draw this arrow as a continuous arrow. Moreover, we will again discuss this point in the magnetic field lines. For the time being, they never form a closed loop, and electric field lines are continuous curve without any break. They do not break at any point when we draw these field lines. And field lines, again and again I am repeating, it is an imaginary concept given by Faraday, not a real. So this is what we have for electric field lines. Now onwards, what will be the advantage of this field line? So I will not be drawing the source. Suppose I draw the field lines like this. Say these are the field lines. Now what is the situation? If I say, what are the sources? Yeah, where the source is and what is the type of a source? So, if these field lines are emerging from these points, someone say, here the sources are positive. Say, in the surface, at the surface, we have positive charges. तो यहाँ सरफेस पे पॉजिटिव चार्जेस है, तो वहां से फील्ड लाइंस क्या होंगी? एमर्ज होंगी. हाउ आई हैव ड्रॉन दिस? अगेन आई एम रिपीटिंग, कीप अ टेस्ट चार्ज एनीवेयर, इट विल मूव अप. So this arrow indicates the direction of the test charge if it is allowed to move freely. So if I draw this arrow, the source can be positive. It may also be possible that some of you may say, take the ceiling as negative. This ceiling is a negative, means ceiling is negative and this is positive. So if I keep a test charge here, test charge is always positive now, and it should be as small as possible. For convention, proton is taken as a test charge, but we call it a unit positive charge. So if I keep a test charge here, again it will move up. If I keep a test charge here, it will also move up. Now if this distance are same, say this distance is same, the force acting on this test charge by the source is same as the force acting on this test charge if the distance is same. So in any case, the test charge will move upward. Either someone will be saying there is a force of repulsion. Here someone may be saying there is a force of attraction. The third possibility can be, again I draw these field lines, same field lines. It should be same distance, though it is not the same distance. We will discuss this also about the electric flux concept. So the distance between the field lines should be same. The test charge placed from the bottom is also same. Now the third possibility may be, here I can draw negative charge, here I can draw positive charge. Again I keep a test charge. So answer would be same. Here someone will say this test charge is repelled by this positive charge, or it is attracted by this negative charge. In all the three cases, the answer comes out to be same. So in the coming days, the electric field lines, while dealing with electric field intensity or electric field lines, the source is there, but it can or it cannot be drawn the source itself or the arrow itself indicates the direction. क्या कहना चाह रहा हूं मैं कि आने वाले दिनों में अगर मैं फील्ड लाइंस बनाता हूं तो there is no requirement for the source. It does not mean कि source नहीं है. Source नहीं होगा तो intensity is zero. Source is there, but you see this three situation. The force of attraction or repulsion comes out to be same in all the three cases. So source does not make any difference to us. And if you remember the characteristic of electric field intensity, it is the magnitude of the source. सोर्स कहां है उससे इंपॉर्टेंट नहीं भाई. सोर्स नीचे पॉजिटिव है, ऊपर नेगेटिव है, कि ऊपर पॉजिटिव है, सॉरी नीचे पॉजिटिव है, ऊपर नेगेटिव, इससे कोई फर्क नहीं पड़ता है फिजिक्स को. व्हाट इज इंपॉर्टेंट इज हाउ मच फोर्स इज एक्टिंग ऑन द टेस्ट चार्ज, व्हाट इज इट्स एक्सेलरेशन, व्हाट इज इट्स वेलोसिटी, हाउ मच डिस्टेंस इट विल कवर. तो क्या इंपॉर्टेंट है? The motion of the test charge is important as compared to what is the situation of the source charge. What is the situation of the source charge? So we will not be drawing the source now onwards. The arrow itself gives us the understanding of the source charge. Let us draw an arrow like this. If I say this is a field lines, someone say the source should be here, positive source should be there. Another person may say for the same arrow कि सर यहाँ पे source negative charge है. However, it makes no difference to the physics because when I place a point test charge at this point P or P dash, the force of attraction and repulsion comes out to be same as compared to this. So source position is important, but not necessary that we draw the source to indicate. Just simply if the field lines are emerging, here it should be a positive charge, where it is terminating it should be a negative charge. And again, if I draw the field lines equidistance, if I draw the field lines equidistance, then this is called as uniform electric field. So if I am drawing the field lines equidistant from each other and parallel to each other, the electric field or electric field intensity will be uniform. And if I draw the field lines like this, later on we will see what happens when the field lines are coming closer or moving away. So clearly here the distance between the field line is large as compared to distance between these three field lines. So this indicates non-uniform electric field. This is non-uniform electric field and this is uniform electric field. So this is how the concepts of electric field lines will be used. And we are concluding the electric field lines that the source, drawing the source is not necessary. The arrow will indicate the direction of the test charge and the length of the arrow gives the magnitude of electric field intensity. Now we have studied the electric field intensity of a single source charge. In the next lecture, we will be discussing the electric field intensity due to system of charges. So we will discuss this due to system of charges. For a point charge, again I am repeating, when our source was a single positive charge, the formula was kq upon r square r cap. But the source was kept at the origin and this can also be written as kq r vector divided by r cube, that is the Coulomb's law in vector form. If the test charge is not at the origin and it has some position vector say r dash, so it can be written as k source r minus r dash, where r is the position vector of the test charge, r minus r dash from the cube. So this is what we have applied the Coulomb's law and divided that Coulombian force by the test charge. So electric field intensity was independent of the test charge. In the coming lectures, we will discuss the last topic of electric field intensity due to system of charges, where in the system there will be number of source charges, say Q1, Q2, dash, 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 Qn. Now this is similar to the superposition principle. You have to simply apply the superposition principle. By superposition principle, we will be finding the Coulombian force and dividing by a test charge, or directly we will be applying the formula for the electric field intensity to do single charge. So in the next lecture we will see about it. Have a good day.